quantum gravity, and let's have some idea regarding quantum gravity. This quantum gravity is a branch of theoretical physics that seeks to unify basically the theories of general relativity and quantum mechanics. And to talk about general relativity, the general relativity was formulated by Albert Einstein, and it describes the force of gravity as the curvature of space-time caused by mass and energy. Now, on the other hand, quantum mechanics, on the other hand, deals with the behavior of particles at subatomic scales, where discrete energy levels and probabilistic outcomes are the basic norms. Now, the unification of these two theories is considered one of the important aspects of physics. At its core, quantum gravity aims to provide a consistent framework for understanding the gravitational force on both cosmic and quantum scales. And now the primary challenge is that general relativity and quantum mechanics they appear incompatible when applied to extreme conditions, like in case of black holes or the very early universe conditions. In quantum mechanics, particles can exist in superposition states, while general relativity predicts a deterministic, continuous space-time. And if we go into the string theory is one of the leading approaches to quantum gravity, proposing that fundamental particles are tiny vibrating strings rather than point particles. So, so loop quantum gravity is another contender which quantizes the fabric of space-time itself. This quantum gravity theories, they often introduce the concept of graviton, a hypothetical particle that mediates the gravitational force, similar to how photons mediate the electromagnetic force. Now, one of the central goals of quantum gravity is to explain the behavior of matter and space-time at the singularity within a black hole. And, and this singularity, the singularity is a point of infinite density where current physics break down and quantum gravity is expected to provide some new insight in explaining the physics around this singularity. The famous Hawking radiation is a quantum effect near black holes, where a pair of particles are created near the event horizon, with one falling in and the other escaping, causing black holes to slowly lose mass. So quantum gravity is also essential in understanding the universe's earliest moments, like Big Bang. The very first moments. So during these extreme conditions, classical physics cannot describe the behavior of matter and energy. And then to talk about cosmic microwave background radiation, a remnant of Big Bang, it holds vital clause for interplay of quantum gravity and cosmology. Now, quantum gravity may lead to the modification of Einstein's equations of general relativity, especially in the regions of extreme curvatures. And, there is certainly a significant challenge in quantum gravity, and that is the development of mathematical tools that can describe space-time at both the quantum and microscopic scales. So theoretical physicists are working on formulating a quantum theory of gravity that can predict phenomena that are observed in the universe, that are observed in the cosmos, that are observed in our surroundings. Now, the quantization of space-time itself implies that space and time becomes discrete rather than the continuous one, right? So some approaches to quantum gravity suggest that the fabric of space and time is composed of tiny discrete units, much like pixels in a digital image, right? So quantum gravity theories, they also aim to address the so-called information paradox associated with the black holes. And, and the paradox question, what happens to information that falls into the black hole as it appears to violate the principles of quantum mechanics? So the resolution of information paradox could provide some great insight into the nature of space and time and gravity itself. This quantum gravity may offer new perspectives on cosmic microwave background radiation and shedding light on universes infancy, the inflation, the start of the universe from Big Bang. Now, in the context of quantum gravity, the universe might have undergone a big bounce rather than a traditional Big Bang that's out there. The Big Bounce theory suggests that universe has experienced cycles of contraction and expansion, and some quantum gravity models propose that universe is eternal and has no singularity as such. There was no beginning at all. And this quantum gravity theories can potentially explain the observed accelerated expansion of the universe. And to talk about dark energy, which drives the universe's expansion, is one of the mysteries that quantum gravity may help to elucidate. It is a mystery out there because it cannot be detected, but its effects can be felt. So the quantum gravity has deep implications for the nature of time itself. The concept of time, may undergo significant changes in quantum gravity. In quantum gravity theories, challenging our intuitive understanding of time, the way we understand time. At the same time, this quantum gravity research it intersects with the study of black holes, thermodynamics, particularly the entropy of black holes. The holographic principles, an idea in quantum gravity, suggests that all the information within a region of space can be encoded on its boundaries. And this quantum gravity theories often involve extra dimensions beyond the familiar three spatial dimensions and one time dimension. Now, these extra dimensions are compactified and not directly observable in our day-to-day lives or in our experiences through experiments. The notion of a landscape of possible vacuum states is central to some quantum gravity theories, such as string theory. Now, this landscape of possible states, it may be plausible that it can explain the fundamental constants of nature and the properties of the universe. Now, at the same time, this quantum gravity research has profound applications, implications for the understanding of the fundamental forces of nature, including gravity, electromagnetism, strong force, and the weak nuclear force. And certainly the search for experimental evidence of quantum gravity effects is ongoing, with some experiments focusing on the behavior of matter at extremely very high energies. This quantum gravity could provide a unified description of particles and forces in the universe, and can simplify our understanding of this cosmos. The development of this quantum gravity may lead to new understanding of the basics, the basics of the universe, the basic character of the universe, the basic forces involved in the universe. These quantum gravity theories have the potential to explain the phenomenon like expansion of universe, the behavior of black hole, the dark energy. But what is important is that the experimental confirmation. So quantum gravity, it's a formidable branch of theoretical physics, which endeavors to unite the principles of quantum mechanics and Einstein's general relativity. It aspires to harmonize the behavior of gravity on cosmic scale with quantum phenomena at the subatomic level. This monumental quest involves the quantization of gravity and the potential existence of gravitons. These are the hypothetical particles, these transmitting gravity. Leading approaches include string theory, where fundamental particles are envisioned as vibrating strings, and loop quantum gravity, which discretizes space-time itself. Quantum gravity's significance extends to extreme environments like black holes, where phenomena like Hawking radiation challenges our understanding. It may also influence cosmology, from cosmic inflation to ultimate fate of the universe. While quantum gravity remains largely theoretical, and experimental verification is arduous, it promises profound insight into the very fabric of the universe, from its smallest scale to its